Those on Zoom, can you hear me?
Yes, I can hear you. Yes, I can hear you.
Okay, so today we are going to continue with different types of sources. Just to summarize, what we saw that last week was after we saw the point charts very early, we saw a charge distributed in a spherical volume. And then we saw a charge along an infinite long line. And then we saw a charge on an infinite plane. And the line charge and the plane charge and the spherical charge were all uniformly distributed. All right, so these were the characteristics. And what we found was that the volume charge, I mean the spherical charge, when you are inside the charge and is distributed, the field goes from 0, and in fact, just to go, let me just remind you, volume module 3. So just to connect with the previous things that we have seen. Okay, wait a second. I lost that for a second. Okay, what's the problem? Uh-oh. There's some problems this morning with Canvas. All right, let me go back to modules 3. All right, and we started with this. And that is the charge that is distributed inside a spherical volume and is distributed uniformly. And we found for this that we solved it inside and externally. All right. And I'm skipping all of these details. I just want to go here. What we found is that inside here, inside the sphere, which is from 0 to capital R, that's the inside space. The field starts at 0 at the center, going up to a maximum value. And then as you leave the sphere and you go away, it goes down as 1 over the distance from the center of the sphere square. All right, the moment you leave that charge, the sphere of the charge, the moment you leave it, it goes down as 1 over R squared, where R prime here, R prime square, R prime is the distance between where you are and the center of that sphere. And the characteristic in this case, it goes like that is because the sphere, of course, is symmetric and the charge distributes uniformly. From there, we went to an infinite line charge like this. And what we found in the solution here, down here, and where it's highlighted, and rho, remember, this is not P, it's rho. And I used rho there, it's the same with R, but I used rho because in the books, the cylindrical coordinates are rho, phi, and z. All right, that's why I use. So rho, this is the not Greek P, not the P, is the Greek rho. And rho is the radius from the axis of the cylinder. So it goes then, in this case, if you are in a cylindrical case, it goes as 1 over the distance, all right? So 1 over the distance square for the sphere, 1 over the distance for the cylinder. And then from there, we went to an infinite plane. All right, let's see. And here we found, when we solved it, that the field away from the plane is constant here. All right. So here I summarize for you before we left last time. 1 over r squared for the sphere, 1 over r for the cylinder, constant for the plane. These are the 3 important things you need to remember. So now we are going to go from, so the sphere, of course, is finite. 3D for a sphere, we covered the finite, but for a cylinder, we had an infinite long. And it's okay to see what happens when it's a line source and it's cylindrical, but in most cases, the sections of line will be finite. So that's what we're going to do today, finite sections of line, and see how to solve this problem. And then we're going to do a charged loop to see also how, because these are very fundamental shapes. And every time you have to solve something, it's going to be either a loop or it's going to be something like a line, finite line charge, or it will be a combination of sections of charges, all right? So a square, for example, there are 4 finite line charges. Then just make a square, all right? A triangle are 3. So you can synthesize different shapes from that. So today, we are going to see exactly, and I will here enlarge this. I'll need to write also. I mean, everything is here, but I need to write so you can understand the progression of what we have done. So I'm writing extra, but that's okay for your understanding. So here I'm going to just take this shape. I don't have to do it over again. This one. No. This one. Copy it. And then come here. Paste. All right. So what I do is the following. Let me erase a number of lines and then I will place them back. So for now, I'm going to erase this to start with the initial problem. Erase this one. Why does that not work? Okay, cut. Okay, cut. And then erase this. Okay. This. All right. So I am here at the observing, as an observant, I'm at a point P. All right, here. And now I want to find out all of this from A to B has a line charge Q sub L, which is uniform from A to B. So if the distance A to B is, say, D, this distance here, or capital L, if you like, call it as the length of this segment of charge, then the total charge here is going to be Q sub L times L. All right, L has the units of length. Q sub L is charge coulombs per length, and total Q is going to be coulombs. All right. Now, this is to put it aside so you remember it. But now I do the following, because this is finite. The field is going to be independent. I mean, so if you look around the cylinder, the field is going to be independent of phi. All right, phi is, if you remember, the cylindrical coordinates. I don't know why it today gives me trouble. Let me see. Oh, I know. Okay, so here, this is Z. Cylindrical coordinates, you remember, is Z, is rho. And if this is the X direction, for example, all right, X, and that was supposed to be Y for the Cartesian system. Rho is the radius, and phi is this one. So in a cylindrical coordinate system, we have rho, phi, and Z. These are the three coordinates, okay? So just to remember that. Now, this phi is different from this one. I've used this because, you know, a lot of books have it. You can use theta if you like. Why not? Let's try to do this here. So use theta here. I will correct it up there. Theta. Okay. So it's independent of phi. So I can move it around like a cylinder. And then it does not matter where around the z-axis I am. As long as I am at the same distance from the z-axis, I will see the same field, all right? So that is important. However, why can we not use exactly the same approach as we did for the infinite z? Because now, for the infinite length, because now our solution depends on z. If, for example, I'm here, if I move point P from where it is up here, but I keep the same distance from Z, the field at P prime is going to be different from what the field is at P. And that stops us, does not allow us to use Gauss's law to solve the problem. All right, so the advantage we had in the infinite line charge is gone because now it's finite along the Z, and then our solution depends on Z. So our solution is a function of both Z and rho. All right, so E that we are looking for at point P now is going to be a function of, this is point P, all right, observant. It's going to be a function of Z and rho, or rho and Z. So because of that, we cannot use Gauss's law. Cannot use Gauss's law. Why is that? Because with Gauss's law, you remember what we were doing? We were finding a whole volume, all right? We were integrating over a volume. And then we were reducing the volume integral into a surface integral using the divergence theorem. And then we were finding this surface where everywhere the field was the same, but there is not one single closed surface here. There is no closed surface in this case where everywhere the field is the same. That's why we cannot use Gauss's law. Okay. Having said that, so here, comment. Now we are going back to this problem and say, okay, I'm now going to use Coulomb's law. Let me call that theta. I will use Coulomb's law to solve the problem, all right? So what do? I, first of all, find the distance of point P, where I am, not from the whole segment, but for Coulomb's law, which is here. Coulomb's law is developed, has been developed for a point charge, for a point charge. So I'm charged at 1 point, all right? You remember that. Now, here the charge is distributed. So what I do is that I find an infinitesimal section of the length AB of the charge. An infinitesimal section is here. I find this. And at that point, the charge is how much? At that point, the charge dq is going to be dz q sub L. All right, you agree with me? It's a uniform distribution. So then I can go to Coulomb's law, and my point charge is going to be dq. All right, so assume now that I have this point charge, then for that point charge, there is an electric field dE, which is given by this formula, 1, and that is Coulomb's law. All right, this is Coulomb's law that I'm using. Okay. What is then next? Since now I found a formula, a differential formula for E, the only thing that I have to do to find the total E is to integrate from B to A along this direction. I integrate from lower values of Z to higher values of Z, all right? From B to A. And I have therefore this integral. Now I'm rewriting this integral in this form. This is just Coulomb's law, but I have integrated over the length of the charge. Okay, then I simplify this to this expression. So I'm bringing, in fact, Q sub L in front, 4 pi epsilon naught in front of the integral. And I have the integral from B, point B, to point A, dz of this expression, which is what is left from Coulomb's law after I moved the constants in front. All right. Now I did that. Let's see how I'm going to find this integral. The best way that everybody has it is to call this angle theta here. And then if this is theta, then rho here. So let me highlight also this triangle. In fact, I did more than that. This one. Look at this triangle here. And then in this triangle, R is the distance of V from dz. Rho then can be expressed in this form. Do you agree with me? This is like what you have from geometry of an orthogonal triangle. All right. So rho is R, which is the diagonal, the diagonal of the triangle, sine theta. Okay. And then also here, theta. I changed it to theta. All right, so I have then that R as which is a vector, obviously, because that's how I have it here in Coulomb's law. R is a vector. So R has this direction. A sub R is its own direction, all right? I use the unit vector to indicate it. And then has a value, which from here, a magnitude, which from here reduces to that one. Okay, so I found for R a simpler form. Now, also from there, I will put it aside here to also show you that not only I know vector R, but I also know its magnitude. And the magnitude is rho over sine theta. Okay? So then I plug in everything. So let me here show you a little more how I plug in things. I will move things when I put them up. So this was a comment that I made here. From here, which is 2 now, equation 2, and equation 1, say in an integral form. So let me call, in fact, these 2, and I call these 3. So from 2 and 3, I go and plug in the values I found for R. So from, yes. R over R squared. This one. Yeah, 3. Tell me the number of the equation. Yes, here. And where are you? Which integral are you looking at? This is here. This one. Okay. What do you want me to explain? I did not do R over R square, R sine theta. You are talking about later. No, here what I found is in that triangle that I've shown you, sine theta is rho over R. Do you agree? Okay. If that is true, then rho is R sine theta. And R is rho divided by sine theta. Oh, we are going back to the integral now. We're not done. Okay. This is so now going back to the integral 1. So from, or 2, like expression of 2 here, the same thing. So now we go from 3 and 2, from like 2 and 3. What do we have? We take this expression 3 and we plug it into 2. And that gives us that E equals Q sub L, what we have, the constant in front, coefficient, then the integral from B to A, and then I will do the substitutions carefully so you see them, and it's going to be vector R is R over sine theta A sub R. So it's R. Let me see. What did I say? Vector R is rho over sine theta, excuse me, rho over sine theta A sub R. This is that part here of the integral. All right. Now I'm going to the denominator, which is the magnitude to the 3rd power. And then it goes the magnitude to the 3rd power of this, which is rho over sine theta to the 3rd. And from here, I have this, and Q sub L is 4 pi epsilon naught B from B to A, dz, and then I have rho over sine theta all squared in the denominator. So practically that gives me sine square theta over rho squared A sub R. All right, that's what I found. This is where I simplified it. This one. Okay, now that's what exactly I have below. So practically now we are going to this equation to solve. All right. Having said that, what you see is that you have the E field along the A sub R direction. All right, so here I show it. So the E field is along this direction. But then I can decompose that into 2 other directions of the Cartesian coordinate system, which is A sub X and A sub Y. All right, so it's easier to solve for these two components of the field, because if the field is along a sub r, it's going to have an x component and a z component, all right? The field is going to have an x component and a z component because the total field is along the a sub r direction. So I'm going to solve for the two components separately because it makes it easier to solve separately. Okay, so I will solve for the a sub x. First of all, a sub x component is along this direction. This direction is, all right? Or in fact, here, sorry, this one is the x direction. All right, so now I will find this component of the electric field. So a sub r decomposes into, let me put here, in fact, theta, change this to make it consistent, theta here, theta. Okay. And then I have here theta. Just to be consistent, I don't want to confuse you with that theta in the cylindrical system, coordinate system, theta 1, theta 2. Okay. And then here also, we have theta prime. All right. So now, a sub r, you see that vector here that I decompose into one x component and the other z component. According to that, a sub r is going to be either in this form or in this form. And this is going to come out of these rectangular triangles. So a sub r is going to have two components. One is going to be along the x direction, and it's going to be cosine of theta prime, which is equal because of the rectangular triangle. Cosine of theta prime is equal to sine of theta. So instead of cosine of theta prime here, I go to sine of theta. And the other one, the z component, which would be, according to this small triangle, sine theta prime a sub z is going to go down to this form. So I write a sub r like this. And then I plug it in again. So now, of course, I go all to theta angles, theta. All right, and then we use some formulas. We're not going to do this. I just want to show it to you now, and then we're going to use only the final formula. But I want you to know how we constructed it. So you use these formulas, all right? The derivative of a cotangent of theta is the 1 minus 1 over sine square of theta. So these are formulas you can find available. Don't need to memorize them. And then I go from theta 1. Theta 1, when I integrate from b to a, theta changes from value theta 1 to theta 2. So I go from theta 1 to theta 2. And this is the integral of sine of theta d theta. All right. And that gives me a very well-known integral, a very well-known function, cosine theta, from theta 1 to theta 2. These are simple derivations. I don't want you to memorize them. I want you to understand them. All right, I'm not going to ask you to write those by heart, but I want you to understand what we're doing. So this way, see here, we were able to find the x component of the electric field. All right, and the x component, remember, is perpendicular to the direction of the line charge, finite, and we found it, which is also important to see. So I will make a comment to remember that. What you found, look at the x. X is the perpendicular to the direction of the line charge. We found that it still varies as one of the rho, which is the vertical distance from the charge, okay, it still varies like 1 over rho, not 1 over rho square. It's not a constant, it varies 1 over rho the same way like it varies for the infinite. However, it's not as simple as the infinite. It has this coefficient, which is the difference between the two cosines. So that's the only difference between the infinite and the finite, that it has this difference in the cosine coefficients, all right? And as a matter of fact, eventually, of course, there is a 4 in there too to remember, but as in terms of varying, how it varies as 1 over rho. And then we can similarly find that for the EZ component, which now we have an EZ component, as before we did not have a Z component. For the infinite long, we only have the perpendicular component that goes away from the cylinder. But for a finite, we have both the perpendicular and the component that goes along the direction, all right? The Z, which is along the direction of the line charge. And this, in fact, is given by this formula. Now, these formulas are very important. I'll show you why, and I will include here a page. I don't want you to memorize how we found them. What I want you to do is to remember how the derivations went, so they make sense to you, all right? So you are not surprised that we have this kind of variation in the field. I want you to understand them. I don't want you to memorize them. In fact, I want you only to understand them and be able to follow the derivations. What I want you to do is to remember these two formulas. These are 3 and 4. I want you not to remember them by heart, but to remember where to go and find them when you have to. And when do you have that example? So let's do an example here. Let's assume that I have a rectangle. Oh, not good. These are here. Okay. Let's make it a little bigger. Okay, I have that. And I'm telling you that this one, A, B, C, and D has the same, of course, sides. It's a rectangle. And this is a charge. It has a uniform distribution of a line charge, which is Q sub L. And then I'm asking you to find the total field at the center, number 1, and they say on the same level with a square, and or in 3D. So this is, for example, is X and Y. And if I do it in 3D, this square is going to look like that. All right. There and there. Yeah. X, Y, and Z. Okay, and then I will, in the beginning, I want you to find it down here. A, B, C, and D. And then I want you to go at a distance and find it up here. So this is what O and O prime. Let's assume that I want you to find the field in these two locations. How are you going to do that? Let's try to do O, which is easier. Okay. To solve this problem, what you would do? You will consider the square to be a collection of 4 sides. all right? They are identical, the sides. You are at the center of the square, and therefore your distance from each side is the same from all sides. The distance from each one of the sides that has not changed. All right, now I want you to find the field at the center. This is X and Y, and there is Z. What did we find in the previous solution? Let's take AB. If we take AB, according to our solution here, we found a component that is perpendicular to the segment and a component which is parallel to the segment. You agree? That's what we found here. Perpendicular to the segment, parallel to the segment. So if I take AB, then AB is gonna create, and let me use this color so you see it, okay? So this is AB, I'm taking this segment. It's gonna create an electric field that is gonna have one component, which is gonna be perpendicular to AB, and the other component, which is gonna be parallel. You agree? Okay, let me go to DC. I'm using for DC a different color. Green. Okay, so I'm going now to DC, which is across. DC is creating how many components? 2. One is gonna be like this, and the other is gonna be like that. So then what? What do these two segments, that one across the other, they carry the same charge distribution, have the same size. They are totally across from each other. What do they do with their fields? They totally cancel. They totally cancel, yes. They cancel. So practically, A, B, and D and C will cancel their fields. So I will erase them. What happens with A and D and B and C? They also cancel. So without thinking very much about math, in this particular case, you can say that the field at O is going to be 0, period. Okay. Now let's go over now the surface. Okay, and there, if you go over the surface, I will only do two sides across from each other. Then in this case, you will say AB, which is red, is gonna create at point O prime 2 components. One is gonna be, let me erase O for a second, okay, and move that to the side. So we are looking up the red. One is gonna be perpendicular to AB. So if I find the center of AB, one is gonna be like perpendicular to AB. So it's gonna be along that direction. And the other is gonna be parallel to AB, it's gonna be that direction. That's what happens up there. What now about C and D, CD like section? Now, in this case, one is gonna be perpendicular to CD like that, and the other is gonna be horizontal to CD. So what happens now in this case? Not all of them cancel, only this one, oops, only this one, okay, let me see. Okay, only this one and this one cancel, all right? But the other two are not opposite, they are identical, but they are at an angle. which means these two practically will give us a contribution. And because they are like this from the z-axis, all right, they create an angle, and then they are symmetric. These two will give only the z component. And then so you go and calculate the ones that are left over, and you find the one component that has remained. I'm not going to solve all of it because I will give it to you as a problem next week. All right. So I would like to take you through steps to see how we solve these kinds of problems. In fact, you have a problem like that next week. So you're gonna, it's not that I will give it to you, I have already given it. So this is how you solve the problem. And then the equations for these two will come from these two equations here. The only thing you need to remember is that whatever components go along the x direction will cancel because of the symmetry of the two sides that you take across. And then the same thing with the other two sides. And then the only ones that are going to give you a contribution are going to be those ones that they are at this angle. And again, these ones, because they are at this angle, the z is the vertical, all right, like the going up and down. Because they are on opposite sides of the z direction, but equal, the only components they are going to contribute to is the z. The other ones, the horizontals, will cancel out, all right? If you have two vectors like this, the horizontals will cancel out, and only the z components will give something. So along the center of this square, the line that goes from the center parallel to z, which is the axis of the square, all right? Then the only component of the electric field that exists is the z component. Okay? And as a matter of fact, the interesting thing is the strongest component. So a lot of times when we go to look at the electric field from this square, we look at that vertical component and not necessarily the horizontal one. But in any case, that we'll see as an application later. So now you can do this problem, all right? You can do a problem of a rectangle. So let's assume that I give you something else, or you find another problem solved like this. Same thing. You take this one as the combination of three segments. And as a matter of fact, the other thing, I don't necessarily want you to solve all of these integrals in closed form. If I give you problems, go and plug the equations as long as I use them correctly, and then either use MATLAB or write your own program to find it, all right, what it is. Here, what I told you a lot of times, to understand the physics, you don't necessarily need to go into a computer immediately. You don't necessarily need to do all of these things. You do them only if you want to give the exact value. But to get an idea that the field that comes out of a square loop is strong along that direction is not something, you know, that you have to go to MATLAB to find it. If you can think about it physically in the physics context, then you have a piece of information that is very important, and you know what you're looking for, all right? That's why we are thinking like that. Any questions about this? Okay. Similarly, I have solved this problem for you, and you can read it here. We are going to cover it next time. And with that, then we have finished practically all of the important structures that you will need to remember how to work with, all right? I don't want you to memorize formulas. I want you to know where to find them. in your notes or in the book. And then I want you to know how to use them. All right, so I'm interested in learning the process and not memorizing things. And the process, I'm interested in having you learn the process as it makes sense physically, not as a recipe. Do not memorize recipes. It's the worst thing. In fact, I have to tell you, I saw when my kids went to school many years back, I saw that math, the way it was taught, is like a recipe thing. 1, 2, 3, 4, like 8 different things. And then they were trying to memorize the steps, and it does not make sense because you don't learn that like this. That's why I'm saying, don't memorize steps. Don't try to see what I've done and try to repeat myself. Think on how I'm thinking. I want you to see how I think physically, because that you will never forget. All right, that's the most important thing I want you to get from this class. Math is a tool. I want you to remember physics. So when you have again, we'll repeat it, a spherical structure with charts goes away as 1/r squared. That applies to antennas. You have to remember that. And eventually you will see it. Now we learned it already. When it is a line like this, whether it is an infinite line or a short line, it goes as 1/ρ, the distance, 1 over the distance from the line. That applies to all circuit lines, to all digital lines, to all RF lines, to every circuit you design. The field that is excited goes as 1 over the distance. And then when you have grounds, when you have capacitors, the field that is excited, if the ground is charged, or if you have a capacitor, we will see this week, then those fields are independent. They are very strong. They are the strongest. They don't care of how far you are from the planar charge. They remain strong. And these are the worst in design, but these are the fundamental things. Then you go to a finite section of line, still the field goes as 1/ρ, you know that. You go to, in fact, even a loop, you will see still goes as 1 over the distance. So it's very interesting to remember. I want you to remember those things and not how to solve the problems, all right? Because you will have all of my notes open. I mean, you can open a book, see how they solve it. But I want you to remember the physics behind it. And so next time we are gonna do this. And then we are gonna introduce 2 things, the voltage or the potential, all right, which is very important. I'm sure you have seen it. Do you remember potential from physics? Okay, which is like the work takes to move a charge from one point to another divided by the charge. But that we use it to create voltage, which is important for us, for electrical engineers, all right, to know what a voltage is. And we are gonna connect that to the electric field, which is important because knowing potential and voltage from electric field and from charge, it gives us what? It gives us the concept of capacitance. Then is extremely important in circuit design. So that's what we're gonna see next time. And then we are gonna talk about shielding on Friday, and we'll do different problems with capacitance, and we'll do more of those problems next week. Okay, so that is how we are going to thematically cover electrostatics. So for electrostatics, the important concepts is how far you go and see the field, and shielding and capacitance. If you could remember those 3 things, that's what I want you to remember in all of the exams we're going to give and everything else. No exercise for Wednesday. I will give you, however, an exercise on Wednesday. Okay? So, thank you.